A-level mechanics, collisions, and Newton's law of restitution. Let's see what Newton's law of restitution is. Well, we'll start by looking at elastic and inelastic collisions. When two objects collide, if they bounce apart after the collision, then it's called an elastic collision. We can see this in the diagram. A ball bounces against a wall and then bounces back. The ball separates from the wall. If the objects remain connected together, then it's called an inelastic collision. For example, if darts are thrown at a dartboard, they stick into the dartboard and don't separate away. So this is an inelastic collision. Newton noted that in an elastic collision, the speed the objects approach each other and the speed they separate from each other are proportional. In other words, the speed of separation divided by the speed of approach is equal to a constant. We can call it e. Or we can write the speed of separation is equal to e times the speed of approach, where e is a constant called the coefficient of restitution. And this is known as Newton's law of restitution. Note, we have e lies between 0 and 1. If e equals 1, the collision is said to be perfectly elastic. The objects separate at the same rate they approach each other. Let's look at an example. Example 1. A smooth ball of mass 1.2 kilograms strikes a wall at right angles with a speed of 4.2 meters per second. It rebounds with a speed of 2.94 meters per second. In part A, we've got to find the coefficient of restitution. Well, to solve this, it always helps if we draw a diagram. We see the ball approaches the wall with a speed of 4.2 meters per second and comes back with a speed of 2.94 meters per second. So, using speed of separation divided by speed of approach equals e, we have e equals 2.94 over 4.2, which is equal to 0.7. So the coefficient of restitution is 0.7. In part B, we're asked to find the impulse on the wall. Well, the impulse on the ball is the change in momentum. I equals mv minus mu. Now, u and v are vectors, so we need to be aware of the signs. The ball initially approaches the wall, so u is positive, but when it bounces back, v is negative. So, I is equal to 1.2 times minus 2.94, take away 1.2 times 4.2, and that works out to be minus 8.568. Because the impacts on the wall and on the ball are equal and opposite, so the impulse on the wall is equal to minus the impulse on the ball. The impulse on the wall is equal to 8.57 Newton seconds. The diagram shows two bodies just before and just after a collision. Now, if we have a problem with two loose bodies colliding, it's useful to apply the principle of conservation of momentum. That is, the total initial momentum is equal to the total final momentum. m1u1 plus m2u2 equals m1v1 plus m2v2. And also it's useful to use Newton's law of restitution. The speed of separation is e times the speed of approach. v2 minus v1 equals e into u1 minus u2. Now this will give a pair of useful simultaneous equations. Let's have a look at an example. Example 2. Two smooth spheres, A and B, with masses 2 kilograms and 3 kilograms, lie on a smooth horizontal surface. A has a velocity of 4 meters per second and directly strikes B, which is at rest. The coefficient of restitution, E, is 0.8. Find the velocities of the two spheres after the collision. Well, to solve this, we can use conservation of momentum. m1u1 plus m2u2 equals m1v1 plus m2v2. Now m1 is 2, m2 is 3, and u1 is 4. So 2 times 4 equals 2u plus 3v. In other words, 3v plus 2u is equal to 8. That can be our equation 1. We can then use Newton's law of restitution. The speed of separation equals e times the speed of approach. v2 minus v1 equals e times u1 minus u2. Now e is equal to 0.8 and u1 is equal to 4. So we have v minus u equals 0.8 times 4 minus 0, or v minus u equals 3.2. That can be our equation 2. So if we take equation 1 and twice equation 2, we get 3v plus 2u equals 8, and 2v minus 2u is equal to 6.4. If we add, we get 5v is equal to 14.4, so v is 14.4 divided by 5, which is 2.88 meters per second. And if we substitute into equation 2, we get v minus u equals 3.2, so 2.88 minus u is 3.2. Subtracting 2.88 from each side gives us minus u equals 0.32, which means u is equal to minus 0.32. So, A bounces back with a speed of 0.32 meters per second, and B moves forward with a speed of 2.88 meters per second. Example 3. A sphere directly strikes a second identical sphere that is at rest. If the first sphere is at rest after the impact, then prove E equals 1. Well, to solve this, the first thing to do is draw a diagram. Let the mass of each sphere be m. Let the initial velocity of the first sphere be u, and the final velocity of the second sphere be v. Now the initial velocity of the second sphere and the final velocity of the first sphere are both 0. So, from conservation of momentum, we have mu plus 0 equals 0 plus mv. So u equals v. Now if we use Newton's law of restitution, we get v equals eu. But v is equal to u. In other words, E is equal to 1. Up until now, all impacts we have considered have either been perpendicular to a surface or two objects colliding directly in line. However, impacts can be oblique, such as a ball hitting a wall at an angle. Let's have a look at oblique impacts. Suppose a sphere with speed u strikes a smooth plane surface at an angle of theta with the plane. The question is, can we find the speed and direction of the bounce? Well, let's suppose the sphere rebounds with a speed v at an angle phi. We can draw a diagram showing the components of the velocity u. Before the collision, along the surface we'll have the velocity u cos theta, and perpendicular to the surface we'll have the component u sin theta. After the collision we've got a velocity v at an angle phi, so along the surface we'll have a component v cos phi, and perpendicular to the surface we'll have a component v sin phi. Because the plane is smooth and there's no friction, during the collision there'll be no force acting along the plane on the sphere, so the components of the velocities will remain the same. In other words, u cos theta equals v cos phi. Now the components perpendicular to the plane will obey Newton's law of restitution. That gives us v sin phi equals E times u sin theta. Now if we divide equation 2 by equation 1, we get v sin phi over v cos phi equals E times u sin theta over u cos theta. Well, the v's cancel and the u's cancel, and sine over cosine is tangent, so we have tan phi equals E tan theta. and so that gives us the angle phi. Now, if we square and add the equations 1 and 2, we get v squared sine squared phi plus v squared cos squared phi is equal to e squared u squared sine squared theta plus u squared cos squared theta. On the left-hand side, we have v squared as a common factor, and sine squared plus cos squared is equal to 1, so we're left with v squared. On the right-hand side, we have u squared into e squared sine squared theta plus cos squared theta. So if we take the square root of both sides, we get v equals u into the root of e squared sine squared theta plus cos squared theta, and that gives us v. Example 4. A sphere strikes a smooth plane with a speed of 8 meters per second at an angle of 60 degrees. It rebounds at an angle of 30 degrees to the plane. Find the rebound speed and the coefficient of elasticity. Well, to solve this, let the rebound speed be v. Resolving along the surface, we have 8 cos 60 equals v cos 30. Now, cos 60 is a half, and cos 30 is root 3 over 2. So that gives us 8 times a half equals v times root 3 over 2. And so we have root 3v equals 8, or v is equal to 8 over root 3. Well, we can rationalise the denominator by multiplying top and bottom by root 3, and that gives us 8 root 3 over 3. To find e, if we resolve at right angles to the plane, we can fill in the angles normal to the plane as 30 degrees and 60 degrees. Then we get v cos 60 equals e times 8 cos 30. Now v is 8 root 3 over 3, and cos 60 is a half, so we have 8 root 3 over 3 times a half equals e times 8 times the cosine of 30, which is root 3 over 2. Now we can cancel the 8 on both sides, we can cancel the root 3 on both sides, and we can cancel on the bottom the 2's. So that gives us e is equal to 1/3. So v is equal to 8 root 3 over 3, and e is equal to 1/3. Let's have a look at a longer question involving direct collisions. Example 5. 3 spheres A, B and C lie on a smooth horizontal plane. A and C have masses 1 kilogram and B has a mass 2 kilograms. Sphere A has a velocity of 9 meters per second, B and C are at rest. A strikes B directly, which then strikes C directly. The coefficient of restitution in each case is E. In part 1a, find in terms of E the velocities of A and B after the first collision. Well, to solve this, draw a diagram for before and after the first collision, and let the speeds of A and B after the collision be u and v. Then, from conservation of momentum in the first collision, we have 9 times 1 plus 0 times 2 equals u times 1 plus v times 2, or 9 plus 0 equals u plus 2v, which can be written as u plus 2v equals 9. And from Newton's law of restitution, the speed of separation is equal to e times the speed of approach. We have v minus u equals e times 9. In other words, v minus u equals 9e. Now, from 1 and 2, we've got 2v plus u equals 9, and v minus u equals 9e. So if we add, we've got 3v equals 9 plus 9e. And dividing all the way through by 3, we get the answer, v equals 3 plus 3e. Now, from Newton's law of restitution, we've got v minus u equals 9e. So u equals v minus 9e. Now, if we substitute v as 3 plus 3e, that gives us u equals 3 plus 3e minus 9e, so u is 3 minus 6e. And this gives an answer, u equals 3 into 1 minus 2e. In part B we're asked, find in terms of E the velocities of B and C after the second collision. We have, before the collision, the velocity of B is v. And let's suppose after the collision, the velocity of B is v dash and the velocity of C is w. Then from conservation of momentum in the second collision, we've got 2 times v plus 1 times naught equals 2 times v dash plus 1 times w. That is, 2v dash plus w equals 2v. And from Newton's law of restitution, we've got the speed of separation is w minus v dash, and that's e times the speed of approach, ev. So if we subtract equation 4 from equation 3, we get 3v dash equals 2v minus ev. In other words, 3v dashed is equal to v into 2 minus e. Now v is 3 plus 3e, so 3v dashed equals 3 plus 3e into 2 minus e, and dividing all the way through by 3, we get our answer, v dash is equal to e plus 1 into 2 minus e. Now we've got w is equal to v dash plus ev, and v dashed is e plus 1 into 2 minus e, and v equals 3 into 1 plus e. So that gives us w equals e plus 1 times 2 minus e plus 3e into 1 plus e. And that simplifies into w equals e plus 1 into 2 plus 2e. And so our answer is w equals 2 into e plus 1 all squared. Now in part 2 we're asked, find the values E can take for A and B to strike again. Now, if A and B collide again, then U must be greater than V dash. That is, 3 minus 6E must be greater than E plus 1 into 2 minus E. So 3 minus 6E must be greater than, expanding the brackets, 2 plus E minus E squared, which can be simplified to E squared minus 7E plus 1 is greater than 0. Well, if we first consider e squared minus 7e plus 1 equals 0, that's a quadratic equation, which we can solve using the formula, or if you've got a calculator that does it in one go, we can get e is equal to 6.854 or 0.1459. If we just draw a graph of e squared minus 7e plus 1, we see that the graph is above the x-axis, outside the region 0.1459 to 6.854, and so it's either got to be greater than 6.854 or less than 0.1459. But E is less than 1, so we have for a second collision, E must be less than 0.146.